Recording. Okay, so a couple things I did want to mention. So we are here on February 9th. Of course, tutorial 4 is due this weekend, and I released tutorial 5 because I noticed a lot of people were working on the assignment yesterday, and it has some tests that you can use for the podcast and episode deep copy and memory management. So yeah, that's out. And then yeah, next week we will talk more about the midterm, and I'll release some practice questions at some point. All right. Any questions on the schedule? What is that? That is something I want to turn off. Okay. So I did want to mention I updated the specification for assignment 2 because there was a couple things that were sort of ambiguous. So everything that's been updated is marked here, but what it is in the network class. I did change when I was, because these things go through a few iterations. So at some point I changed get subscriber to has subscriber because I realized I didn't ever need to get subscriber, but then I didn't change it in the UML. So get subscriber is deprecated. You should have a has subscriber function that returns a Boolean, and also a get podcast. So get podcast was in the UML before, but it wasn't in the specification. So I just added it to the specification. So, and this is stuff that you probably could have, as I said, when you run into these kinds of discrepancies, often you can just use common sense and figure out this is, probably what I meant. It's difficult to release a document this size without mistakes, especially when you have somebody else to look at it. When you do a class with another instructor, it's much easier because it's easier to spot somebody else's mistakes, right? But I can look at that 100 times and my brain just fills in the blanks, and it's so finding errors is not unusual. You can always ask questions, and you can always use common sense. I'm not going to punish you for that. All right. Questions on that? All righty. Okay, so last class we were talking about, let me get over here and let me turn off my camera so I don't have that. All right, it's going to be picky today. 1 second. Okay. All right, so last class we were talking about object-oriented design and not UML class diagrams. So we will get to UML class diagrams today. But yeah, first we want to talk about object design categories. So we've done a lot of the technical foundation, not all of it. It's almost endless with C++, but we've got a good strong technical foundation. Now we're going to look a little more into design, and one of the things we are going to look at is object design categories. This is sort of short, and at the end we'll do an array example, which covers a lot of the material from assignment 1, the bonus material, such as adding things in alphabetical order and removing up to a certain point and things like that. Okay, so in this set of slides, we'll give an overview. We'll talk about types of object categories, and then we will go into our example in collections classes. So what are object design categories? Really, again, all of these things apply at scale. When you're writing small programs, a lot of these ideas go out the window, right? As your programs get bigger and you have to handle more, let's say, clients or data, then object-oriented design and design in general becomes a lot more relevant. There's nothing worse than over-designing a small program and realizing I didn't need all that stuff. Anyway, so when you get to these bigger programs, what happens is a lot of the objects tend to fall into categories, right? So when we talk about these object categories, this could be a good starting place for good design for a bigger program. So yeah, ostensibly, or at least at scale, each object we make should kind of fit into one of these categories. Now, there's always exceptions, but generally speaking, most applications will, of course, each object will take on one of these. So each category has a specific responsibility. And then once we, look at the different categories, it's easy to think of classes that could go into that category. We've narrowed the scope now, and now we're only handling one responsibility, right? So now it's easier to think of a class that I can use in that category. And also classes within each category should be single purpose and reusable. We want our programs as modular as possible. Okay, so the type of object categories, I'm going to relate these back to assignment 1 loosely, of course, because assignment 1 does not quite neatly fall into these, but entity objects. So these would be, say, a student or a room object. These are essentially low-level objects that contain data about some real-world object. There's not a lot of application logic, maybe a few things. But mostly it just holds, this holds the name and student number. And if it was a real student object, it would contain a few other things. And then maybe, some application logic for sorting, things like that. But that's it. We have our control objects. These would be, in some sense, the library class or the global test functions, which, are not really a class. So again, assignment 1 doesn't break down quite that neatly. But library sort of handles the interaction of the other objects. We have our boundary objects. These are sometimes called view or user interface objects. So this is the boundary between the code and the user. So we can present an interface to a user, or maybe we present an API to another piece of code. And then there's collection objects. So up until now, we've been using arrays. But of course, in C++, they have vectors, and they also have a bunch of other stuff that, everybody kind of goes to vector right away, which is, vector's nice, but it's not all they have. All right, so this might start to look a little bit like model view controller. It's not meant to be. Model view controller is a design architecture meant to, solve a specific problem, which is, well, we're not going to get into that right now, but it uses the observer design pattern. It looks similar to these object categories, but it's not the same. Object categories are in some sense broader in scope. So yeah, these are categories typical of application objects. So it just helps us design. Helps us to design our programs. And also in smaller programs, we have classes in multiple categories. That's perfectly normal. Again, over designing is its own problem. Okay, so entity objects. So these would generally model real world objects. We talked about students, we talked about rooms, or information tracked by the program. It could be sales, things like that. These often represent persistent information. So this is, in some sense, the data of our program. So stuff that we save in between sessions. So real world objects, university might be more of a, depending on the application, university could be a control object, but if I have a database of universities, then this could be an entity object. But, student, instructor, these could be entity objects. So basically information and small amounts of application logic. Control objects are in charge of the program flow. So what code is executing, what classes are interacting. Now we had in assignment 1, we used a main function, and then we made a library object and then passed it into these test functions. So library was kind of a control object. We had control, I guess, test functions and rather than control objects. But for assignment 2, we have test control and test control, which is a control object. So yeah, it handles what code is executing, what classes are talking to which Yeah, network would also be a control object. Yeah. Again, so I guess sort of the premise behind assignment 2 and most of the assignments we do here is that we're making an application. It's not quite complete, but we're going to run some tests on it. So that's sort of the, it's sort of it's not, of course, our podcast network doesn't really work, but I thought it would be more fun than doing something realistic. So yeah, when we talk about control objects, the network would be a control object. In a finished application, but we introduced an artificial one. All right, so yeah, they control what code is executing, what classes are interacting, and how they're interacting. So in assignment 2, test control asks test view to get some input from the user, and then based on that input decides what tests to run, right? So that's sort of the control flow. So typically your object-oriented main function in C++ has 2 lines of code. We create whatever the, I guess, root of our control objects, since there could be multiple control objects, but the root of it all, we create that and then we launch some function on it, right? And that's sort of the top level control object. It creates all the other objects and controls how they interact. All right, yeah. So that's there. Boundary objects manage the interaction between the application and foreign entities. So in assignment 2, that would be our test view would be a boundary object, right? So we are taking input and what tests to run, and then it just passing that information back to the control object. So yeah, boundary objects can be other programs or interact with other programs, or they can interact with users. It could be an API or a user interface. So for instance, Facebook, right, has an API. I can build my applications on it. That API would be, or those objects would be boundary objects that are part of that API. All right. So ideally, you want to keep all of your boundary objects separate from, things that are more core to application logic. So how I communicate with outside entities should not be affected by how I do my other jobs that I'm supposed to do. And that, of course, that loose coupling makes it easier to swap out one interface for another. Okay, and collection objects. So for a collection object stores multiple entities of the same type, right? So in some sense, these are like a database, similar. So we also can have functions for relevant behaviors, right? We might sort, retrieve, process, whatever things we're storing. We have up till now used primitive collections, so primitive arrays. So arrays are essentially just basically a chunk of memory. So there's very little associated behavior with them. You have the subscript operator. See, I finally looked it up. It's no longer square brackets. It's the subscript operator. Very little associated behavior and little to no error checking. If you subscript something that runs off the end of the array, well, that's on you. The array is not going to check that. But another example of primitive collections would be a class, right? So I can make a class or use, let's say, a vector class. This is backed by some other collection. A vector is backed by an array, as we'll see when we get there. And that has, that influences how we would use vector and whether we store objects or pointers. As you'll see, we probably want to store pointers. So yeah, this other collection could be another class though, right? I could make, we're going to make an array class that's backed by an array, but I could make an array class that's backed by a vector, right? And then I can have all of the same interface. I can have all of the same functions, but they're just, running through a vector class instead of a primitive array. So yeah, these classes can let us add behavior, error checking, control access, things that are relevant just to collections, also things that might be relevant to our application. Yeah, so why not just use arrays? Probably you're starting to get some idea of why not. They're difficult to work with, they're error prone, and they're static, at least in the context that we're using them. We could, of course, have them grow and shrink the same way the vector class does, for instance, but we're not doing that in this class. You'll do that in 2402. Collection classes would, any collection class worth its salt grows and shrinks as needed. So why do we use arrays so much? Well, we need the practice. We need the practice, but also a couple other reasons. When you're using a vector class, if you understand how the arrays are being used, it will stop you from making mistakes that would slow down your program and or cause memory leaks. But also, if we make our own collections, we would maybe use a backing array, and then we can make it as fast and efficient as we need to. All right, so collection objects in general are an excellent example of good object-oriented programming. And they're a good example of also of encapsulation and abstraction. So as you'll notice, when we're using arrays, there's a lot of details, right? So we have to keep track of where things are in the array. If we remove something, we have to close the gaps. If we add something that's in some sort of sorted order, then we have to make room for it. There's a lot of details. So we want to abstract away those details and present a nice, simple interface, like say add, remove up to some item. And this also encapsulates this array, right? I'm hiding the fact that I'm using an array from you. I'm just giving you the interface. And if at some point in the future I want to change my array to a vector, I can do that. It's not going to affect the interface that I'm presenting you with. All right, so let's make an array class. We're going to make an array of students. So here is my student object. It's an entity object, very simple. It has a little bit of information about students and a little bit of application logic in this less than and a print, of course, and a get name because we need to be able to compare one student to another. So we're going to use the names to do that. All right, so that's should be straightforward. There's the implementation in case you're interested. But again, it's very, very bare bones class. So we're going to make an array of students. So this is the start. So this is the abstraction of an array made explicitly for student pointers. The next step would be to abstract it even further and use templates, which means that instead of adding only students, we could add any type of data. So that's, we will get there eventually. We're not there yet. But let's say, well, first of all, we want to store students. We need some sort of backing data structure. So we're going to make a student array. We're going to make a dynamically allocated array of student pointers. So essentially, I just declare a double pointer, and then all of the initialization is handled in the constructor. Of course, I also want to keep track of the number of elements in this. We'll say use a size variable for that. Okay, so now what kind of interface do we want to present for our collection class for students? Well, we want to, of course, add students. We're going to use here. So yeah, we're going to use a Boolean as a error indicator, right? So if this returns false, this means I did not have room to add this student. If it returns true, that means the add was successful. So as I do these operations, I can just check to see whether this returned true or false to see if it worked or not. Somebody mentioned for the getters specifically that we could use a null check. So let's say we also want a get method, but we want to identify the student. We're going to identify the student using their name. I'm going to here. Actually, let's keep this simple for now. Okay. So, and then I want to return parameter. So I need to pass a student pointer. I want to return a student pointer which means I have to pass a student pointer by reference, right? And so to do that, I pass a double pointer. Okay, so somebody mentioned that instead of having a true false here, I could return, if this didn't pick up anything, I could do a null check, right? I can return null in this pointer and then just check to see if it's null. That's perfectly valid. We're not going to do that here. There's no real philosophy behind it other than we're going to practice these different techniques. We'll do it a different way when we get to linked lists. What else do we need? Well, let's say we want remove. So again, we want to remove the name by name. Typically for a collection class, when we remove something, we also want to return that thing. So we're going to delete the student from our array, but we're not going to delete this dynamically allocated student object. We're going to return it, and whoever is using this array class can decide whether or not they want to delete it, right? It would be, let's say I had a vector class and I add a bunch of student pointers. When I remove one, I don't want the vector class to delete that because maybe I'm sharing that with somebody else. So those types of decisions should not really, I can implement them in this, but it's really kind of limits the use cases, right? So now I can't use that anywhere where I'm sharing, these pieces of memory. So as a general rule, you don't want to assume that you should delete something in a collection class, although we are going to delete things in the destructor just to keep it easy. Just because this was one of the bonus questions, we'll say remove up to string name. So on the assignment, it was remove up to some date. In this case, we're going to remove up to some name. So everybody, if we say remove up to Drake, then, Alice, Bob, and Charlie will be removed, and, Phil and Trent or whatever would still be left there. And then we want to print. We don't need a Boolean here because this will, it's possible that we remove nothing, but that's the behavior we want. So we don't actually care. This will always succeed in some sense. All right, so that's our, this is our class interface, and our backing collection. So any questions so far? Okay, so let's implement some of these now. And this is nice. At this point, if I'm a user, I know nothing about how this is implemented, but I know, I can very easily add, get, remove items from here, remove up to a certain item and print everything out. So how they're implemented, I don't care if I'm using this class. We care because we're writing it, but nice clean interface that does everything, an array would do, except for we could also add get by index, but we're not doing that right here. Okay, so here I want to initialize my double pointer. So I want to make a dynamically allocated array of student pointers. And I believe there's a max array preprocessor constant that I'm going to use. So yeah, my max array here, because I include the .h file, I can use it here. And I want to initialize my size to 0. All right. So yeah, now I have an array in my destructor. Since I have a new in my constructor, I should have a delete in my destructor. So at the very least, I want to make sure to delete this elements array, right? So I see new here, and I see new with the subscript operator, then I delete with the subscript operator, at least that. Also in here, although I said it's a bad practice, I'm going to delete all the student objects just to keep our, just for this example, just to keep things clean. So to delete all the objects, first of all, I would delete before I delete the array. and then I can use a for loop. Int I equals 0, I is less than size, plus plus I, and then delete elements at I. Okay, so again, this is not, you would not normally do this in a collection class. We're going to do this because I don't want to manually delete everything every time. All right, so we're managing our memory well so far. I think that should be pretty straightforward. Questions on this? All righty, so let's make our, so what's a good one to start with? Let's make the get function. That's probably the simplest one to start with. We're assuming that we've added some students at this point, and now we're going to get a student with a specific name. So bool array, we need the scope resolution operator. We're going to get some student with the string name, and we're going to return it to our stu pointer that's passed by reference. All right, so now how am I going to get it? So, well, let's take a look here. So we have an array in memory. It's actually, you know, we have a main function, let's say, and we make an array. Let's see, this is the array object. And then on the heap, we have a backing array, right? So this is an array of pointers. All right, so I'm going to delete all that and just look at the array of pointers. So at this point, I've added some stuff, and even though I'm adding in alphabetical order, I want to keep everything pushed as far to the front as possible. So everything looks like this, and the size, the size looks at this. So 0, 1, 2, 3, 4, 5. I have size equal to 5, so size points here, and I have, of course, 1, 2, 3, 4, 5 objects in my array. So when I want to add, you know, if I added something to the back of my array, I would add it at location size. But in this case, I simply want to run a for loop and look at every object up till here, up to size, and delete all of them. Or sorry, I want to look at every object up till size, and I want to compare it. So if I say get C, then I will look at A, and then I'll look at B, and then I'll look at C. I see that C matches, so I'm going to return the pointer to C. Now, this is a sorted array, so I could use something like a binary search, but I'm not going to do that. I'm just going to do very, very simple. So essentially, I want to do something very similar to what I did on the delete, except, so I'm going to copy this for loop, but instead of deleting everything, I'm going to compare it to my name string. So if the name is equal to the elements, arrow operator, get name, well, then I found the item I'm looking for, assuming that name is a unique identifier. See, that's what I like about Visual Studio Code as opposed to using just a text editor, is that it showed me I was missing a bracket, whereas I would have been searching for that otherwise. Okay, so if the name is the correct name, then I'm going to assign that to my output. So I'm going to dereference my pointer. So this, I dereference a double pointer. This returns a pointer, and I'm going to assign this memory location. Where am I? Okay, so this is the one I want to return. And then at this point, I can simply end all of this and return true. I cannot type today to save my life. I mean, normally it's bad, but today is extra bad. If I loop through everything and I don't find the name I'm looking for, I want to return false. All right, so that's our first function done, right? So very simple, loop through everything. I check every element. Once I find the one I'm looking for, I assign it to my output parameter, and I return true. All right, questions? Okay. Now, these ones are a little more difficult. So we'll start with the add. Or maybe I should start with remove. Now let's start with add. So bool array add student pointer. So we're going to add stu, but we need to find the correct location to add stu in. So let's see what I use here. Yeah, I used a for loop. Yeah, I think that should be fine. All right, so the first thing we want to do is check to see if, oops, I'm in the wrong place. So we're going to check to see if our array is full. So if size is greater than or equal to max array, then we return false. Now somebody mentioned, well, isn't this sufficient? And logically, that's true. If I've written all my code correctly, then the only time I would never have a size that is greater than my maximum array. However, if there's a bug in the code that I accidentally increment size twice, then maybe this is a good idea. So I always sort of, assume that I could have made a mistake somewhere. All right, so I've done my check. At this point, I'm going to loop through the array. Okay, but let's look at what we want to do here. So I want to add here. I want to add something in alphabetical order. So I have A, B, D, E, and I want to add C to that. So what do I want to do? Well, let's say I started looping at the beginning. I say, well, C doesn't go here. C doesn't go here. I see D. I know it has to go before D. So how do I put C in there? Well, I have to move E over and I have to move D over. And then I have to come back and put C here. So I could do that. There's nothing stopping me from doing that. I can just remember this index. Once I get to the proper place, I just shift things to the right and then insert C. But what I'm going to do instead is I'm going to start at the back and I'm going to loop to the front. So I'm going to say, I'm going to compare C to E. I'm going to say, well, C is less than E. So I'm going to copy E over here, and then I will move to the next location. So I will compare C to D. I can see that C is still less than D. So I'm going to copy D into E's old location. And then I'll move to the next location. I see that B is less than C. So I know that C must go here. So I'm going to put C in there. So that's what we're going to do for this. So that means I want to loop. I want to start at the back, size, and then I want to loop to the front, which means that I'm going to check that I is greater than 0. And we'll talk about specifically why I chose these values instead of size -1 and maybe greater than or equal to here, int I. There. In a second, but for now, okay, so I start at the back and now I'm going to loop front to the front until I see something that is less than my current element. So if, I mean, my typing has become pathological at this point. Less than. So I'm going to use this less than function to keep things sorted. Yeah, so I'm going to compare it to the current element. Actually, I'm going to compare it to the element just before. So I start at size. If I look at size, this location technically holds nothing. So I'm going to start looking at element size -1. I have to pass in less than takes a reference to an object. So I have to dereference this to get to the object. So if it's less, then I found where I need to, actually no, as long as it's less than this current object, then I still need to keep moving elements to the right. So I'll say elements I equals elements I -1. Otherwise, I have found where I need to put my current object. So I'll say elements I equals stew. Right, so I've gone down, I found the one that comes just before the location where I'm supposed to put stew. So I found the element that's less than stew, or sorry, I found the element that's greater than stew. No, I found the element that's less than stew. Am I doing this wrong? Yes. So if stew is less than the element, then I do this. If the element is less than stew, then I do this. That's right. Okay. So I found the element that's less than stew. So now I'm going to put stew just to the right of it. At which point I can increment my size variable and return true. All right. So far, so good. However, what can happen is I can go through my entire array. If I say add, all right, so this is, let's say there was something that came before A. Let's say I have B here, and I put add A. Well, then my for loop is going to go right. It's going to check here, check here, check here, check here, check here, and then I'm going to bounce out of the for loop. I'm not, without having added my A. I've copied everything to the right though. So I've made space at the very beginning, right? So everything has been copied to the right. So if I come out of the for loop without ever returning true, that means I need to add it to the first location, 0. And then I can increment size and return true. Okay, so that will add things in alphabetical order. Should we have some check to make sure the array isn't already full? What would happen if the last element is full? Yeah, so that's what the first line does, right? This makes sure that this, so I didn't put any comments in here. When you, the code that's on Brightspace has comments. So actually I didn't comment this line. Check if array is full. So yeah, because in the first step, I'm moving something to the right. So I have to make sure there's space for it. But yeah. What happens is the last element of a full array? Yeah. So if it's full, we return false. So do we need to consider the situation in which the student is already in the array? Not in this case. That's, you're getting into, well, first of all, yeah, you have to decide about duplicates, if you want to store duplicates or not. So we're assuming that we can we're either assuming we store duplicates and the remove function just removes the first one it finds, or we can assume that we're only ever given unique items. But you know, either way, this is not going to be a complex collection. So yeah, we're just going to kind of hand wave it. Other questions? All right. So the remove is a little more complicated. It's similar to the, student. So we need an output. So in some sense, we have to find the student before we remove it. So it could look a lot like the get, and I could use a for loop, but I'm going to show you how to do it using a while loop for a couple of reasons. One is because you can use a while loop. And I think in this specific case, the while loop reads a little easier. All right, so first let's take a look at what we're going to do. So of course, the first thing, we have a name. Okay, so no, we don't need to do any error checking. So let's see what happens when we remove an object. So yeah, A, B, C, D, E, F. So let's say we remove C. Well, again, we're simply going to start at the beginning and look at each one until we find the one we're going to remove. However, when we find it, of course, we have to assign it to the output parameter, right? But then we want to start copying everything one to the left, right? So D is going to be copied here, E is going to be copied here, F is going to be copied here, and then we can leave this pointer here and just decrement the size variable at that point. So we are going to start at the beginning. We're going to go up until the point where we find what we're looking for, at which point we start copying. So we could do this with an if statement inside a for loop, or we can use 2 while loops. So one while loop will take us to where we find the thing, and then the next while loop will take us to the end, copying everything one to the left. If we're using a while loop, though, we need to manually keep track of our index. Sorry, index 0. We could use I here as well, but we'll use index to make it more clear. And then we will say, yeah. So we have to check for 2 conditions. One, we have to make sure while the name is not equal to elements at index. So here we're checking to see, we want to, here, first of all, inside the while loop, all we're going to do is increment the index. So this is just walking forwards. So what we want to check is that while we have not found the one we're looking for, we keep walking forwards. There's a problem in that maybe the one we're looking for is not in here. So what I want to do is also say index is less than size. Now, this is the code that I gave you, and there's a small subtle bug in here. Anyone spot it? Right, what happens? Yeah, so at some point, index gets to be the same size as size. Well, yeah, what's going to happen is if I run off the end of the array, so I start at index equals 0, let's say that size is 2, just to keep it simple. So index equals 0, this is fine. Index equals 1, this is fine. Index equal 2, well, what happens here? This gets checked before this one does. So now I'm trying to check the index, the element at index 2, and this is empty, and I get a segmentation fault because there's nothing here. So yeah, what I have to do is actually, the nice thing about these logical operations is that it will evaluate this first, and if this is false, then it does not evaluate this one. So this comparing index first is safe, memory safe, because I never have a segmentation fault if I run off the end of it. But yeah, I do have to check that first. There was you might have a very old version. I've updated it. Well, I updated it once to do while loops. Yeah, the first one I did was a for loop, and I didn't really like it. It was kind of ugly. Yeah. Okay, so at this point, I've either run off the end of the array. So I want to check to see if I've run off the end of the array. So if the index is equal to size, I'm going to return false. I did not find the element I was trying to remove. That means this still holds garbage. Oh, I should put Stu here. So yeah. Otherwise, I did find the name. So now I've walked through up till I found it. Now I'm going to insert the element, or sorry, grab the element. So I want to put this current element into my output variable. All right, so I found this returns true. So instead of incrementing the index, I bounced out, I assigned it to this student variable, at which point I have to go walk through and continue walking through to the end. And I want to move everything one to the left. But actually, I'm not going to go right to the end. I'm going to go one before the end. Because if Stu is in the last place, then I don't need to copy anything. So yeah, if index is equal to size -1, then this while loop won't even be entered. But in the meantime, I copy everything one to the left. Oh, sorry, I'm not using I, I'm using index. And then I can increment my index variable. Okay, so at this point, I've copied everything over. I can say decrement my size variable and return true. All right. Just questions about that? I haven't tested anything yet. Could be mistakes in here. Okay, let's make sure this works before we do the last one. We'll do the last one a little bit quick. So here's my main function. I have, I statically declare an array. Of course, this statically declared array makes a a dynamically declared array of student pointers on the heap. And then I'm going to declare a pointer here just for, you don't really need to, but it doesn't hurt. So I'm going to add a bunch of students, right? And I could just call add and then put this rate in, supply it as an argument. That's fine. But so I'm going to add a bunch of students, and it should be clear what the alphabetical order is here. And I'm going to make sure that it comes out in alphabetical order and there's no mistakes. Okay. Did I print? Oh, I don't have a print function. Print function, straightforward. I'm just going to do a for loop over everything. And then print it all out. Oh yeah, and it's complaining because I didn't put my scope resolution operator in here. So it has no idea what these variables are, but now it does. Okay, let's try that again. Okay, so Alice, Bob, Cindy, Zeke, and the sleepy student, and everybody's in alphabetical order, even though we did not add them in alphabetical order. So it seems like my add function works fine. And I can test this with Valgrind because I have deleted everything in the destructor. All heap blocks were freed, no leaks are possible. So I've done everything correctly up until now. All right, so good. So our add function works. We also made a remove function. Oh, we have a get. So let's do our get. So we're going to take, I have get student, it's supposed to be get. So I'm going to take my student pointer, which, yeah, before we do that, let's just say s equals null. All right, and then I'm going to pass it in here. So what I really should do is say if this returns true, then I'm going to print this object, else So if I find Cindy, I'm going to print out I'm going to print Cindy out. If not, I'm going to print out Cindy not found. It should find Cindy because we did add a Cindy. Okay, so here getting student Cindy, we print out, we found her and we printed her out. So yeah, everything's great so far. All right. The last thing we had is the remove. So instead of getting Cindy here, let's remove. So in this case, yeah. So if we find Cindy, we will print her out. And then afterwards, we will print out our array to make sure that Cindy's no longer in there. This I am less confident of, but let's see. Okay, so removing Cindy, we found Cindy, we removed her, and then we printed out the array. We have Bob twice. We have Bob 3 times. So yeah, I did something wrong there. I know what I did wrong. Did anybody else spot it? So I obviously copied Bob. I took Bob and I copied Bob over everyone, which, yeah, not a good idea. So this is in my remove, and this is the second while loop. This is copying everything one position to the right. But I copied one position to the left. So I did copy everything one position to the left. Or to the right. I should have copied everything one position to the left. Right. So this would take the one in index +1 and move it to index instead of, so that's a shift to the left rather than a shift to the right. All right. Okay, so remove Cindy, and then we print out everyone, Alice, Bob, Zeke, and Zzz, and Cindy's no longer in our array. So that seemed to work correctly. Yeah, just to make sure that we mark what we're doing and when. So yeah, Alice, Bob, Zeke, and Zah. We can check that with Valgrind as well to make sure that we've been handling our memory correctly. We definitely lost something. What did we lose? What did we lose? What were we supposed to do? So our remove function does not delete Cindy. It just grabs a pointer and returns it. So we should delete that object before we exit. So it still works. We use it with Valgrind. All heap blocks were freed. No leaks are possible. All right. Questions so far? Okay. All right. So let's do remove up to, and then we'll do that kind of fast. So this would have been the bonus array. So we want to remove up to some name in alphabetical order. So this is going to look very similar to our remove with a couple of key differences. First of all, we don't have to return anything. Yeah, that's fine so far. Let's focus on this first while loop. So what do we want to do? If we say we want to remove up to we want to remove up to D, let's say. Up to D. So, and let's say we're going to, do we include D? I think we include D. So what we want to do is we want to keep searching. We see here, we want to remove A because A comes before D, so we're going to delete A. Then we go to the next one, we see B, we delete B. We go to the next one, we see D. This is, we delete D because it's less than or equal to what we're looking for. And then we see E. E is greater than D. So what we want to start doing is copying the rest of them down the same number. So we removed 3. And since we deleted 3 items, we copy everything down to 3. All right, so that's sort of what's going to happen in this. I'm going to speed it up a little bit. Where are we? So in here, instead of, we still want to increment this, but we want to delete at the same time. So we want to delete and increment in one step. So yeah, this walks through until we find what we're looking for. And instead of not equal to, we'll say greater than or equal to. Okay. At which point we want to remember how many things we removed. So we want to make a toRemove equals index. So this is the index is now the number of things that we removed. And then we want to say while index is less than size, in this case, we'll say elements at index minus toRemove. So we're moving everything, this number of items to the left equals elements at index. And then, yeah, that's size minus equals toRemove. And then we don't need this return. So very, very similar to the remove with a couple of key differences. We simply have to, this would work for if we removed, in some sense, this is as if toRemove was just one item. But now we want to remove this many items, so we have to, I've changed the indices a little bit here to make it more clear, but for add function, could it run off the end of the array? For add, we do a deliberate check in the beginning to make sure that we don't run off the end of the array. Yeah.
Mind if I just chime in on that?
Sure.
Yeah, maybe it's just because I'm looking at it backwards since we're starting at size and not starting at 0. So we go, I see the size comparison to max array, and then we start size I and then I greater than 0 and decrement.
Yep.
And then if S is less than what is at elements I minus 1. So when we go all the way down, maybe I'm getting my order of what happens in a for loop mixed up, but when we go all the way down to I equals 0, oh, never mind.
Yeah, it only
it
goes
helps to talk.
Yeah, for sure.
Yeah,
yeah, no problem. And that's really for these loops, that's the trickiest part, is getting those off by one. Those off by one errors are hard, and you really have to, sometimes you have to test for them deliberately. So yeah, obviously I wrote this before, I tested it. I made mistakes the first time I wrote it, and I rewrote it. So yeah, I have the benefit of, being prepared, but yeah, it does help to talk through it for sure. All right, other questions? Okay, let's make sure this toRemove works. So what do we do here? So instead of remove, we'll remove up to Cindy, just for fun. That means we don't need this. And we don't need an if since it returns void. We actually just remove everything up to Cindy, which includes Cindy. although that is, you know, a design decision. It could be everything before Cindy. So we're going to move everything up to Cindy and make sure that we get the proper output. So we're moving up to Cindy. So we removed Alice, Bob, and Cindy, and all that's left is Zeke and this fella. Let's check with Valgrind to make sure that we deleted everything correctly. So yeah, all heap blocks were freed, no leaks are possible. Okay, so remove and remove two, you could have also used for loops, and instead of, so I used two separate while loops to indicate, you know, one was up until we found the item and one for after we had found the item. But you can use a for loop and then an if statement inside the for loop to check to see if we found the item yet or not. So you can check to see if I should be, you know, copying things over or still looking for both of these. So I could have an if that says, if, you know, we haven't found the item yet, just increment. If we have found the item, then we're going to do this and also increment. All right, and you guys have a copy of that code currently on Brightspace. If you have an old one, it doesn't have the remove up to, and it uses a for loop, but the for loop is a little bit uglier. All right, that's a lot of technical details. Any questions though? All right. So we will get started on UML, looks like. So a general sort of idea behind object categories, right? If you can imagine a beer store application, so you would have a beer object, which would be the entity object. It would store information about each individual beer item. I'll answer that in a question. Sorry, in a second. If we have a point of sale at the cash register, we would have a boundary object there to interact with the cash register, right? And then take that information and return to the control object. The beer store would be the control object, so it would handle the interaction of the cash register with the stock or the inventory, which would be the collection object, right? So a very simple application with 4 classes and 4 objects might look something like this. I did start writing this and then it didn't turn out the way I liked. So plus I don't really have a cash. I didn't really want to make a cash register a whole thing. I had other things I had to do. So, all right. Is there a difference between ++I and I++? Yeah, we're going to see when we get to operator overloading that this is actually more efficient for one. The other thing it does is it increments it first. If I said A equals ++I and A equals I++, well, let's say that I is equal to 2. In this case, A would be equal to 3. And in this case, A would be equal to 2. In both cases, I would end up being equal to 3, right? So this is the prefix operator. This is the postfix operator. And the prefix operator does run a little bit faster, as we will see. Okay, other questions? Yeah, a lot of technical details at 8:30 in the morning. All right, so let's get a start on class diagrams then before we go. 40, so 15 minutes. Yeah, it should be. All right, so we're going to talk about documentation. We're going to talk about the importance of documentation and some of the different types of documentation. And then specifically in this class, we're going to use class diagrams, UML class diagrams. So there's an example in assignment 2 and in assignment 3. You're going to read the specification, you're going to write the code, and you're going to write a UML diagram for that code. Okay, so documentation in general. So documentation can be tedious. I guess I don't want to take too much time here, but so I don't come down super hard on commenting, in your assignments, because I found it in the past really hard to get TAs to mark it consistently. So it's either I say, okay, you comment every function, and then it's easy to mark, I guess. But the problem is that what I don't like about that is sometimes people wouldn't comment a function, and I'm like, no, you shouldn't. I mean, two people could be given the same function, right? And one can write 3 beautiful lines of code that you read and go, I know exactly what's happening. This code is self-documenting. I do not need a comment there. You can put one, but you don't need one. Whereas somebody else, like maybe me, I come in, I use a for loop that spans 20 lines and a bunch of if statements. Well, probably there I need to add some comments to say, here's what's happening in this part, here's what's happening in this part. So I don't really like saying that, oh, I absolutely need a comment for this function. Well, it depends on how well you write it, really. So, and for myself, especially, comments, I used to hate it, but once you write enough code, you realize, oh man, it really does help to have even just a couple of lines of, yeah, here's what's happening here. So that's, as far as comments in the code goes, that's why I don't really try to enforce it. I recommend you do it. I recommend you comment everywhere you think you need comments. And I hope as you program more, you'll gain an appreciation for it, but it's difficult to get it. I didn't really like the way, I didn't like deducting people marks because they didn't feel they needed comments. And I agreed with that. I didn't, but it's hard to make it consistent. Anyway, documentation can be tedious until you come back and try to modify your own code. And then you go, no, it's actually really important. And if you're trying to use a library or a language with poor documentation, oh boy, that's fun. Trial and error. So first of all, guess the function. I don't know. Does it look like this? And then guess what it's supposed to do. So yeah, I've worked with Lua was one. There's some documentation, but it wasn't really complete. I had to do a lot of, I write a function and then put a lot of print statements and see exactly what's being changed inside of it. And then, yeah. Contrast that with a language like Java, right? If you Google anything in Java, you get this nice sort of Java wiki. It has a documenting utility built in. I can just, instead of compiling my code, I can compile the documentation for my code. It's great. And that is sort of the experience you should be aiming for. When somebody reads your code, they should not be confused. It should be very clear what's happening, especially if you're making a library. Yeah, exactly. So yeah, somebody mentioned they had comments that took more lines than more lines of comments than lines of code, which is, yeah, I don't feel like that's useful. So yeah, you will, if you program long enough, hopefully you will gain an appreciation. Okay. So yeah, another thing that can happen on the job, you have a lead programmer who's a superstar, who's doing everything. They get a better job. All of a sudden, oh, how do you pick up where they left off? Well, you hope that they put comments on their code, right? So you got to think, when I'm writing a program, I'm communicating with the machine, I'm communicating with the computer. I should also be communicating with other programmers, right? So whether that's, nicely labeled variables and functions or comments, you should think that somebody else has to read this. So, yeah. So types of documentation. So this is the a software development lifecycle. Typically goes requirements analysis. You sit down with the client, you see what they need, you figure out how you're going to meet those needs. A design, the design stage where you sort of make you plan out, especially if it's a big piece of software, you kind of plan out beforehand, what kind of subsystems will I need? What kind of objects will I need? Then you get to the implementation. So in some sense, the assignments are, I've done this and you guys are doing this. And I've written a couple test cases for you. So the implementation would be, I'm giving you this, this document, the specification, and you're implementing it, and then running some tests to make sure that it works. But tests themselves should also have different documentation. So all of these requires their own documentation. This would be comments. This is a spec. This is, well, you'll see that in 3004. It's a nice, big, thick document. Okay, so requirements analysis consists of functional requirements. This is like, for assignment 2, I should be able to download a podcast, right? That's a functional requirement. And you specify exactly what that means. So this is what your system will do. Non-functional requirements might be that it should run on Linux. When I download a podcast, it shouldn't take more than 5 seconds, something like that. Use cases, you model the interactions between the user and the system. Okay, so I have a network. How do I connect with it? Well, I have a client app on my phone. So I open the client app. What screen should I see? If I want to download, is there a menu there? Do I make a menu selection? So this is sort of the use cases. You sit down and you walk through each possible scenario. High-level object model, you start to make a plan, right? At high level, you say, oh, I'll need something that communicates with the network, and I'll need some, I'll need a podcast and a episode class. So you think about the major entity, boundary, and control objects. And then, the dynamic mode, system behavior from an external point of view, right? So maybe a set of instructions for somebody to be able to use my application. All right, in the design stage, we have a subsystem decomposition. So I break things down into high-level subsystems, right? So in some sense, this is similar to the object categories, but a little more fine-grained. Detailed object model, like for instance, a subsystem might be, if I have a point of sale, interact with the cash register. This will have a bunch of duties. So I have to figure out what those duties are. And then I start with the detailed object model, where I figure out the low-level objects that would be involved in this cash register subsystem. Then in the implementation stage, which is what you guys do, you should have program comments, intelligent naming conventions. I guess I've hopefully outlined clearly my philosophy on that. So when you would be docked for comments is essentially if there's a piece of code that the TA cannot understand, then they can subjectively deduct marks. They have to justify it. But really, that's, I think, the best strategy is if you confuse the TA, then you should have had some comments there. Or, better naming conventions. But, it's okay to have messy code as long as you explain what you're doing at this stage. Testing, so we should have a test plan and test cases. So an overall test plan. We'll get into the more details in a second. So your code should be self-documenting. It should hopefully read like a story. That's what I tried to do for the remove function, changing the for loops to while loops to hopefully give you more of a sense. That plus the comments I feel like would be easier to understand, plus the pictures, I guess, although it's still pretty complicated. But yeah, hopefully when you read somebody else's code, you get a sense of exactly what's happening. So comments should describe the purpose of every class. I'm not overly concerned with that, but details of complex or critical class members, for sure. If you write something really complicated, that's sort of unusual, you should have a few comments there so that the TA shouldn't have to trace through all of your code. You should be able to take a look and say, okay, this is what you're trying to do. It kind of looks like you have the right idea. I'm not, they're not there to debug every aspect of your code. They're there to see if you have, I guess they're there to see if you have the right approach. Test cases should describe what portion of the program you're testing, the input and the expected output. So I more or less do that. So, I give you some tests. They're a little bit ad hoc because they're what I used when I tested these assignments, and I just gave you the same tests. So, you know, I could be a little more organized about my test cases, but I suppose it's better than nothing. Unit tests, right? So I take pieces of my program and I test them individually. So we've done some of this in our tutorials. We've tested the room, we've tested the tutorial 5, we test the podcast and episode classes, things like that. Systems testing, this is also known as integration testing. I take a bunch of subsystems and I put them together and then I test them, right? So this is sort of like our test control and test view from assignment 2. And another example of, integration testing is, when you design a game, you write a game, you give it to a game tester, they play it. This is your entire system working together, and then you find a bunch of other bugs that you didn't know were there, or the game testers do, and they document it. All right, so class diagrams are a type of documentation that use the Unified Modeling Language, or UML. So when we want to document basically low-level subsystems, also higher-level subsystems, we use class diagrams. So these are used to represent object-oriented models. The syntax is not always agreed upon. It depends. Wherever you work, we'll use some specification. There's a bunch of different ones. So this helps document our object-oriented design. It's basically a communication tool. We're going to start using it more and more after today. It's supposed to be programming language independent. The idea is that whatever I write in UML can be implemented in any object-oriented language. We will see, though, that you do get into there. It's tough to do that perfectly. There are language-dependent things that you do introduce. As far as when you guys write your UML for assignment 3, you can refer back to these slides. This will be our specification. We're using a very, very small subset of UML. It's just to get you started. So there's not a lot of things that need to be described. So yeah, this is our specification. Okay, so different types of UML diagrams. So we are going to be doing the UML class diagram. So we're going to detail attributes and operations. This is also assignment 2, is the UML class diagrams, and the associations between the classes, right? So these classes interact. How do they interact? Does one contain the other? Do they just talk to each other? What have you? There's also, you will see these in 3004. We're not going to see them here, but activity diagrams, sequence diagrams, swim diagrams. This is documents the behavior of your program, how the classes interact, what messages they pass back and forth, and how that, makes sure that the proper thing is happening. UML state machine diagrams. Sometimes your application can be reduced to a state machine. So this is helpful for that, right? So if you write a program for a Coke machine, for instance, a Coke machine is essentially a state machine. So I put in coins. If I put in a quarter, it reaches the state of contains 1 quarter. Anyway, you'll take that in. You may or may not take that. I think theory of computation is optional now. All right, so UML is for object-oriented languages, not procedural. So you wouldn't use this for C. It's supposed to be OO language independent. So in some sense, this is an abstraction of an object-oriented program. So we don't include things like global functions. We don't include constructors, getters and setters and things like that. In our classes, we document the attributes and the operations and the associations. So I could have an is-a relationship between 2 classes, right? So when we get to inheritance, a has-a, a has-many, is contained by, etc. All right. So how far do we get? All right. Well, I guess that'll finish us off for today. So next class we will finish. There's not a lot more to go on. We'll finish UML diagrams and start on encapsulation. So encapsulation, we will talk about const. So for assignment 2, I hope you did use const string and for your. We are sort of expecting this instead of string. But yeah, next class we will talk about why we expect that instead of string. But that's it for today. I can stick around to answer a few questions, but otherwise I will see you guys on Friday.